Hi all, this is going to be the first video on topic 6, which is about electric and magnetic fields, but in this video we will only focus on charges, Coulombs law, the electric field, the electric potential, and so on. So let's kick this off. So the title of the video is electric fields. Magnetic fields will be covered in another video, okay? So what happens when we have free charges? If we have free charges in space, they will either repel each other or attract each other depending on their polarity. We have two types of charges, positive and negative, okay? So let's write this general statement down. Free charges attract or repel each other. Okay, so let's write this down. So let's say we have a positive charge Q1 and a positive charge Q2 separated by some distance r. Then Q1 is going to exert a force F to the right because they repel, and Q2 is going to exert the same exact force but to the left on charge Q1 because they repel. Same happens, the same is the case when we have two negative charges, minus Q1, minus Q2. They repel each other by the same amount. But if we have, say, a negative charge minus Q2 and a positive charge plus Q1, then they attract each other by the same force F. Now, what's this F given by? This is something that you probably saw in other physics classes. So F is the popular, F is the popular Coulomb's force. It's a vector, so I'm going to use the hat for now. Given by K, Q1, Q2 over R squared. The Coulomb's force acts in the direction connecting the two charges, and obeys Newton's third law. I'm gonna write it as N3, Newton's third law. And we can see this here. This is the line connecting the two charges, right? So the force is along this direction. Okay, and if F is the force exerted on Q2 due to Q1, then F is also the force exerted on Q1 by Q2. Therefore, Newton's third law is obeyed. Now let's go talk about the constant K. K is given by 8.99 times 10 to the 9 Newtons meter squared, coulombs to the minus 2. This is a huge constant in comparison to the gravitational constant, which we will use in a moment just to demonstrate how strong the electromagnetic force is. Another constant usually used in electricity and magnetism is epsilon naught, defined by the following. So we can write K as 1 over 4 pi epsilon naught. If we solve for epsilon naught, we will find 8.85 times 10 to the negative 12 farads times meters to the minus 1. Farads is a unit used in capacitors. We are not gonna deal with that for now. We will be mostly using K. So let's go see an example demonstrating how large this force is. So let's take the example of two protons inside a nucleus, okay? So when we deal with protons, sorry, I'm having my coffee. So in a nucleus, protons are separated by about 10 to the negative 15 meters or 10 femtometers. So in a nucleus, protons are separated by r equal to 10 to the negative 15 meters. So, and I remind you, this is something we studied in at the A-level physics. So let's choose blue. So if these are the protons, the nucleus is a blob of matter that looks like this. So where these are the neutrons. Okay, it's a very compact object. Therefore, protons are really close. And just to give you an idea of how close they are, in an atom, which is also tiny, I'm gonna put in parentheses here. In an atom, in atoms, protons in the nucleus and electrons are separated by 10 to the negative 10 meters. So the atom is about 1,000,000 times larger than the nucleus, and the atom is also tiny. So, okay. Anyway, so let's go find what the Coulomb force between two protons in the nucleus is. So F Coulomb is K Q1 Q2 over R squared. And Q is 1.6 times 10 to the negative 19 coulombs. That's the charge of one electron, or here we write positive electron because protons have positive charge. So if the charge of one proton is 1.6 times 10 to the negative 19 coulombs, then F Coulomb is 8.99 times 10 to the 9. By the way, when I do numerical calculations involving units, I usually put the numbers to the left and the units to the right, okay? It makes it cleaner. So what are the units for K? These are the units, we saw that earlier. So I'm gonna put that to the right, newtons, meter square, coulombs to the minus 2. And then we have Q1 times Q2 is E squared, because we have two protons. So 1.6 times 10 to the negative 19 squared, Coulomb squared. And then I divide, and I divide my units too, it's the same thing, over the separation is 10 to the negative 15 meters. If we take the square of that, that's 10 to the negative 30 meters squared. And here with the units, we get nice cancellations, as you can see. So the Coulomb force between two protons comes out to be 230 newtons. Think about that for a moment. 230 newtons is the weight of, say, a dog weighing 23 kilograms. Okay, that's a huge force for such tiny particles. Okay, now let's go see. This is something you learn in Unit 5, but I'm gonna use it here. So the force of gravity between two masses is given by F, actually not G, let's call it Fn, and it's called N because it's the Newton's law of gravity, okay? So Fn is G m1 m2 over r squared, where G is the gravitational force constant, and it's equal to 6.67 times 10 to the negative minus 11 newtons meters squared. So up to this point, we have the same units between K and G, okay? And, but then instead of Coulomb square here, we have kilograms to the minus 2, right? So just by inspecting the constant, we see that this is tiny compared to the electric constant. So the mass of one proton is 1.67 times 10 to the negative 27 kilograms. So Fn is G, it's 6.67 times 10 to the negative 11, and then I put my units to the right, times the mass of the proton is 1.67 times 10 to the negative 27 squared kilograms squared, and then I divide the units as well, over 10 to the negative 30, and then meter squared because the separation is the same. Okay, so this force turns out to be 1.86 times 10 to the negative 34 newtons. So if I divide F Coulomb by Fg, I find about 10 to the 36. So the electric force is 10 to the 36 times larger than the gravitational force. Okay, so imagine if this was the dominant force in nature. It would be a very violent universe. So in nature, most things are electrically neutral, especially in everyday life. Like we are electrically neutral. The same goes for the houses we live in, etc. Okay. So gravity is the dominant force, which is really weak compared to the electric force. So far we have been talking about charges and the forces they exert on each other. Now let us see and discuss the concept of the electric field. So I'm gonna start with writing a general statement. So when dealing with large or complicated charge distributions, it is convenient to work with electric fields. And the electric field is denoted by E, and I put an arrow on top of E to denote that this is a vector quantity. So let's study the electric field and the concept of the electric field via an example. So let's say that we have a large metallic sphere. Maybe it's a Van der Graaf generator. You guys are probably familiar with Van der Graaf generators. So those are used to charge a small metallic sphere. So maybe it's a couple of centimeters in diameter, and you can deposit a lot of charge on that sphere, okay? So plus Q, BQ is the charge of the large sphere. And let's say that we have a proton plus Q, which has a charge of plus E. And this proton is in the vicinity of the large Q, the large metallic sphere, which is charged. So what's gonna happen? The proton is gonna be repelled by a force F to the right due to the positive charge plus Q. And the proton is gonna be pushing the large metallic sphere plus Q to the left. But obviously you immediately see that the proton is the one which is gonna move, not the large metallic sphere, right? So let's keep this thought in the back of our minds and let's go write down what F is equal to. So F is just Coulomb's force, which is equal to K BQ small q over r squared, where it is implied that Q is much larger than small q. Okay, again, whenever I use the larger than symbol twice, I mean that this quantity is much larger than this quantity. Now let's divide. So let's divide F by the small charge Q. Okay, so this is now a definition. E, the electric field, is defined as this force, Coulomb's force, divided by the small charge Q, and it's given by KQ over r squared, measured in newtons per coulomb, since we are dividing a force by a charge, so we get newtons per coulomb. Right, so some of you are gonna object, so why not divide F? So let's define E subscript small q as F over BQ. Immediately we see that we divide by a large charge, so we will get KQ over r squared. So yes, indeed, actually every electric charge sets up an electric field, but it doesn't make sense to talk about the electric field of the proton, which is gonna be, because it's gonna be much smaller. So E small q is gonna be much smaller than the E we just defined over here, okay? And this is because this is a much larger charge, okay? Now, I'm gonna jump to unit 5 again and talk about gravity, because how can we think of E? E is analogous to G, which is our familiar gravitational field constant, which is equal to 9.81. And I'm gonna write this in units of newtons per kilogram. Okay, this is something that's maybe unfamiliar to some of you. Let's quickly see that newtons per kilogram are equivalent to meters per second square, because 1 newton is 1 kilogram times meters per second square, but we are dividing by kilograms, so we get meters per second square. So E is analogous to G for electricity. How does that make sense? So who is setting up that gravitational acceleration? It's the whole of the planet Earth, pretty much, okay? So G is set up by Earth, which has mass big M, okay, equal to 6 times 10 to the 24 kilograms, okay? Now, what's my mass? I mean, my personal mass is 80 kilograms, okay? So 80 kilograms times 9.81 is about 800 newtons. So a mass M, small m, will feel a force, which is the weight, right, equal to mass times G in the vicinity of the Earth, right? That sets up that gravitational field. So the same applies, but for charges in electricity. So in the vicinity of a large electric field E, a small charge Q is feeling a force Q times E. So in the vicinity of E, a Q feels a force Q times E. What is that force going to do? Since F is ma, then Q times E is m times a. So this little charge Q is going to be accelerated by an amount a equal to Q times E over the mass of the particle, okay? So just like a mass is accelerated in the gravitational field of the Earth, a charge is accelerated in the electric field, in some electric field E. Okay, now we said that the electric field is a vector quantity, okay? So as a vector quantity, it has both magnitude and direction. How do we find that direction? By using a small positive test charge that we put in the vicinity of the electric field. So using a small, this is like a thought experiment, by the way. So using a small positive, it's always a small positive test charge. I don't know why. You can as well use a small negative test charge, but nobody does that. We use a small positive test charge. So using a small positive test charge in the vicinity of E, we can find its direction. So if I have, say, a spherical charge distribution with charge Q, it sets up an electric field E, right, in all space. So if I put a small test charge there, then it's gonna be pushed away in that direction that connects the center of the sphere with this test charge. If I move my test charge here, it's gonna be pushed out like that. if I put my test charge there, it's going to be pushed out like that. By the way, the force is going to be stronger near the charge and weaker away from the charge, the big charge Q, okay? So, and let's do one more thing before we move on. And if the charge is negative minus Q and I put my test charge plus Q there, now it's going to be pulled towards the negative charge. And this pull is going to be stronger near the charge and weaker away from the charge, okay? So this is the concept of, so it is actually convenient to define electric field lines. So these arrows pointing towards this big charge minus Q or pointing away from the plus Q charge, those are electric field lines, okay? So electric field lines show the direction of the force experienced by a test charge, by a test positive charge, small q. So they never cross, they are denser if E is stronger. And why would E be stronger? Because it has a large amount of charge, large amount of charge. Okay, now let's examine a more complicated charge distribution. Let's say that we have a parallel plate positively charged, and across that we have a plate that is negatively charged. And yes, this is a capacitor that we will study at some point. So if I put my test charge here, okay, let's put it here, plus Q, and let's see what's going on, what kind of forces is going to experience from the top, the positive plate. So if I take a small amount of charge contained in this piece of the plate, this is going to push my charge Q in that direction. But diametrically opposing this small, this, let's call this dq, and let's call this dq as well. So this little piece of the plate is going to push my charge in this direction. I can analyze the force experienced by plus q into horizontal components, and you can immediately see that they cancel, and vertical components which do not cancel, okay? So the electric field between the space of these two plates is going to be pointing down vertically from the positive to the negative charge, okay? So this is how you find electric field lines. So by the way, if I go back, no, I don't have space. So let's write this down as well. So electric field lines go out, go out of positive and into negative charge. Okay, let's go see another example. So let's say that I have a plus Q and an equal and opposite minus Q charge somewhere in space, okay? And this is my plus Q. Now, what kind of force is it going to experience? From this sphere, it's going to be like that. And from this sphere, it's going to experience a force pulling it down that way. So this is the component of the force that this charge is going to experience. If I put the charge there, it's going to experience a force like that. If I bring my charge over here, it's going to experience a force there because it's closer to the negative charge than the positive charge. And in general, we can just draw the electric field lines like that, okay? This is what the situation is going to be like. So again, you see that the electric field lines go into negative charges and out of positive charges, okay? And by the way, I didn't mention it yet, the electric field lines are perpendicular to these spheres, okay? It's not obvious the way I drew it here, but they are perpendicular. And let me show you guys something I find cool. So let's go to this website. I'm gonna provide the link down below. So this is by the University of Colorado, and it shows you cool simulation. So in this simulation, you can see the electric field set up by positive and negative charges. So let's create a grid. Let's also have values. So you see that 2 boxes are equivalent to 1 meter. Let's go put a positive charge there. So you see the electric field lines that get weaker as we move away from the charge. And if I put more charge, the electric field becomes stronger and stronger and stronger, okay? Now, let's put a positive charge there, okay? And let's put a negative charge close to that, okay? So this is the situation that we were just talking about, okay? Electric field lines go out of positive charges and into negative charges. And if I put other charges, I get weird distributions like that, okay? You can play with that and see what happens, okay? Now, let's go back to our notes and talk about the concept of energy needed to move a charge. So let's go talk about that. Energy needed to move a charge. Okay, so force is Q times E, and as we saw for point or spherical charges, that's K Q Q over R squared. But the work needed to move something is given by force times distance, right? And if for a moment we pretend that that is equivalent to R, okay, from a charge, then if we use this, we find that the work needed to move around a charge is equal to K Q Q over R squared times R, so K Q Q over R, okay? We call this the electric potential energy, and it's equal to K Q Q over R, and it's the energy needed to set up this charge distribution. So electric potential energy is a scalar which tells us the energy stored in some charge distribution. Okay, so this is kind of like an intermediate step to help us talk about the next definition, which is the definition of the electric potential, which is also very significant in electricity. So electric potential. Okay, so with electric potential energy and electric potential, we move away from vector quantities and we start talking about electricity in terms of scalars. And by the way, this has units of joules, okay, because it's an energy. So KQQ over R is an energy measured in joules. So the electric potential, I'm gonna jump into the definition immediately. So definition, V is the work needed that we were talking about earlier over Q. Which Q? The small q, because again, we use the same concept of having a large charge Q that sets up an electric potential in the vicinity of which a small charge Q can be found, okay? So the electric potential V is given by work over Q, and what is work? It's this quantity over here. So it's K Q Q over Q R, so Q cancels, so K Q over R, okay? Is measured in joules per coulomb, and 1 joule per coulomb is 1 volt, okay? The familiar volt that you use and you see in your batteries, and this is a scalar quantity. Scalar quantities are useful in physics because they don't involve a direction, so they are easier to work with. So what does this electric potential tell us? What does this quantity tell us? So electric potential is the energy per unit charge required to move a charge in the vicinity of an electric field. So, for example, if we have a potential of 1 volt, which is 1 joule per coulomb, and a charge of 1 coulomb, then we will need 1 joule to move that 1 coulomb through that electric potential, okay? Just like we did with the positive test charge in the case of the electric field, let's write down that in the presence of V, a positive test charge small q has energy equal to EP equal to Q times V. Okay? Let's go see the significance of this electric potential. So, and also talk about the equipotential lines. So let me start a clean page. So, significance of V and equipotential lines. So if I have a charge plus Q, then if I have my positive test charge at position 1 and at position 2, it will have a potential V1 here and a potential V2 there. Now, if I am at the same distance from Q, my charge is also going to have a potential V1 anywhere around that sphere, and then the same goes for this big sphere, okay? I ran out of space. So the energy here or here or here or there is the same, which tells me that I can move my charge around this circle for free without spending any energy. And if I am at position 2, I can also move my charge from there to there or there or there along the circle for free. I don't need to spend any energy. But if I want to move my charge from position 1 to 2, I need to spend energy. Okay, so this is the idea. And this, by the way, are called equipotential lines because around those equipotential lines, the potential is the same. This is why it's called equipotential. And to go back to the gravitational field, when you walk on a leveled surface, you have the same gravitational potential. Your gravitational energy does not change. But if you go upstairs, for example, if you walk up some stairs, then your potential energy changes, okay? So if, and let me go back to using black color, sorry. If plus Q moves from V1 to V2, then it will acquire some energy equal to Q times V1 minus V2, which is going to be equal to its kinetic energy. So, for example, if I have a test charge, a positive test charge, if it moves from 1 to 2, it will have some kinetic energy, right? And what is that kinetic energy going to be equal to? It's going to be equal to the difference between this potential V2 and the potential V1. So let's go see this through an example. I have Q equal to 10 microcoulombs. R1 is 10 centimeters. R2 is 15 centimeters. Actually, this is my big Q, sorry. Comma, and my positive test charge is equal to 1.6 times 10 to the negative 19 coulombs, which is plus E. Then as we said, Q times V1 minus V2 is equal to the kinetic energy. And let's assume that this is a proton, okay? Proton. Then 1.6 times 10 to the negative 19 times V1 is equal to 8.99 times 10 to the 9 times 10 times 10 to the negative minus 6 over R1 is 0.1 meters, okay? Minus, so this is going to be V1 pretty much, okay? At a distance of 10 centimeters away from this big charge Q. Minus 8.99 times 10 to the 9 times 10 times 10 to the negative 6. It's the same thing, but now over 0.15. Okay, this is V2. Okay, this is going to be equal to 1/2 times the mass of the proton, which is 1.67 times 10 to the negative 27 times V squared. And if you guys do the math, I'm not going to show it here because it's going to take time. You find that pretty much if we put a proton here, okay, it will move outwards, and by the time it makes it, if this is R1 and this is R2, by the time it makes it to R2, it's going to have a velocity of 2.27 times 10 to the 6 meters per second. Okay, that's a large velocity. Now, we talked about the equipotential lines, but let's write it down. Equipotential lines means that V is the same along equipotential lines. Equipotential lines are perpendicular to electric field lines. And equipotential lines are complicated for complicated charge distributions, okay? So let's go see one complicated charge distribution. So plus Q and minus Q. I'm not going to draw the whole situation, but remember the field lines look like this because a test charge is going to move along this line. Sorry. And they look like this in away from the center and like this, and they go into the charge on this side, etc. So equipotential lines are lines along which the potential is the same, and they are perpendicular to field lines. So if you can picture this, if you draw lines perpendicular to the electric field lines, you will get something like this. And these are gonna look like ellipses, okay? Something like this. And the same goes here and here. I'm gonna show you the demo, it's gonna help. So, and in the middle, for example, you'll get a straight line, okay? because that's the only option pretty much of drawing a line that is perpendicular to the electric field lines. Okay, the next topic I want to talk about is equipotential lines and how they grow apart, as they say. So equipotential lines grow apart. So let's do a silly example. So we have a charge plus Q, and let us assume that the potential here is 1 volt, very close to the charge. Then let's assume if that's 1 volt, then the 2 volts is gonna be over here. The 3 volts is gonna be further out, okay? So you immediately see that the increment is 1 volt, but you cover more distance to find the next equipotential line that increments the initial volt by 1 volt. So the more you move outwards, the easier it is to move away from the electric potential. This is what I mean by equipotential lines growing apart. Okay, so you cover, you have the same increase in electric potential, but you move a further distance out. Okay, so it appears in questions. So yeah, that's the idea. Now, notice, let's talk about one more thing, and then I'm going to show you a cool simulation. So notice that V is KQR, therefore if we take minus dV, the first derivative of V with respect to R, we're gonna find KQ over R squared, which is the electric field. This is no coincidence. So another definition for E can also be defined as the gradient, negative gradient of V. So E can also be defined as minus dV over dr, and it's we said that it's measured in newtons per coulomb, which is equivalent to volts per meter, because V potential is measured in volts, which is joule per coulombs, right? And R is measured in meters, so E is also given by, can be measured in volts per meter, okay? Now, what's the significance of that? So let's say V is a scalar quantity, okay? So, and let's say that we plot V with respect to R. So we will get a line that looks like this, okay? What does this tell us? That as R increases, the voltage decreases, which makes sense because voltage, if we were dealing with a point charge, is equal to KQ over R. Okay, now the slope of this curve is the electric field. So the slope over here is, or the gradient, is 0, right? Why is it 0? Because far away from the electric charge, we have no electric field, right? So, but by the way, the negative gradient is the electric field. So the negative, so the slope here is negative, but the negative of a negative is a positive. So the electric field here is stronger, and it gets stronger there, and it's very, very strong near the charge, which makes sense, right? So the slope of the gradient of the voltage is the electric field, okay? And the last thing I'm going to talk about before moving on to showing you a simulation is that for uniform fields, this definition of the electric field comes in handy. So for uniform fields, and the uniform field is the field we saw earlier between two parallel plates, which looks like this, okay? So these are the electric field lines. And by the way, the equipotentials are equally spaced like that, since equipotential lines are perpendicular to electric field lines, Okay, so for uniform fields, if the distance between the plates is d, then using the definition of minus dv over dr, which can be cast into minus delta v over d, okay, we can, if we know the voltage between these two parallel plates, for example, if we put a battery of 1.5 volts, I'm sorry, and the distance between the plates is 10 centimeters, then we can find the electric field. All right, now let's go see the simulation and finish this off. So let's clear the screen. So remember that we can put a grid and values. So earlier we were interested in the electric field. So for a moment, let's pretend that it doesn't exist and let's plot the voltage. See? And this is a voltmeter, by the way. And this is a ruler, okay? So this is 1 nanocoulomb. You can put the meter on top of the charge so that you can measure the distance from the charge. Actually, the arrow should go there, okay? So now you have a really neat tool to play around. So this is 1 meter away from the charge, for example, okay? So this tells us that the equipotential there has a voltage of 8.47 volts. And I think you can press that, okay? And it puts the equipotential, okay? It draws the equipotential. So the potential here is 4.45 volts, for example. If I draw it, it looks like that. I can draw another one here. I can draw another one there, 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 etc. So you can do things like that. It's kind of cool, okay? So, by the way, let's go find, remember when I told you about, you can do calculations, guys, by the way. So the voltage here is 17 volts, okay? So anyway, you can play around. And let's put other charges here as well. So if I put 2 charges here, and let's put 2 charges there, I can draw the equipotential lines that look like ellipses. Remember I told you about that, okay? And I advise you to, guys, actually calculate things here and play around, and it's gonna help you understand better. So this is it for this video. I hope it's not very confusing, okay? Let me know in the comments what you think. Like, subscribe, tell your friends.